All right, we are in section 2.5 today. We're talking about the chain rule. And the chain rule is another derivative rule to add to the growing list of derivative rules that we have covered so far. So we've covered several of the basic ones, the product rule, quotient rule, etc. And today we're doing this new one, the chain rule. And this one is arguably the most important one, just in the sense that it seems to show up or be necessary more often than the others. And not only that, it leads to some other techniques that we're going to talk about later in this section. So to motivate this rule, suppose we're dealing with a function of the form, or like this, y equals the square root of x squared plus 1. This function will resist any of the techniques that we know so far as taking its derivative. The product rule, quotient rule, the sum rule, difference rule, all of the different things that we have talked about won't work when we try to take the derivative of this particular function. However, the chain rule, which we're about to talk about, will manage to deal with this. And the chain rule specifically applies to what we call composite functions. Functions that are formed by using function composition. So if we define two functions related to this one, so f of x equals the square root of x and g of x equals x squared plus 1, then this function can be written in the form f of g of x. Notice that f is kind of like the outside function. F is the thing that takes an input and square roots it. So that's what's happening here. We're square rooting something. G of x represents what I'm going to be calling the inside function. The x squared plus 1 is what we're putting inside that square root to make this function right here. So that means that y has this form to it, f of g of x. Now, composite functions, provided that f and g are differentiable functions, can always be differentiated using the chain rule, which looks like this. If I want to take the derivative of f of g of x, that's equal to f prime of g of x times g prime of x. So basically what this does is it takes this function, differentiates or takes the derivative of the outside function, but still evaluates that at g of x. You notice the g of x here and the g of x here have not changed. But then in addition to that, that new function is multiplied by the derivative of your inside function. So sometimes I refer to this as inside, outside, inside. So we start by writing our inside function. That gets plugged into the derivative of our outside function, and then all of that is multiplied to the derivative of our inside function. So returning to this previous example, how then do we find the derivative of this? Well, we've already identified an inside function and an outside function. And in the chain rule, we end up needing the derivative of both of those. So if I find f prime, the derivative of the square root of x, we have done multiple times now. It's 1 over 2 times root x. And then g of x, its derivative would just be 2x. That's from the power rule. So g prime of x equals 2x. And then what I want to do is use my chain rule with these derivatives that I just found for f and g to put everything together into the correct derivative of y, the function that we started with. So the chain rule says that this is equal to f prime of g of x times g prime of x. This is f prime right here, 1 over 2 root x, but we use it in function composition. I take g of x and plug it in for that x right there. So that becomes 1 over 2 times the square root of x squared plus 1. Then we multiply by g prime, which is 2x, so that's times 2x right here. And then oftentimes there's going to be one simplifying step. So when I multiply 2x to this 2 and that 2 will cancel each other out, and the x here multiplies into the numerator, so I get x over the square root of x squared plus 1. This guy right here is the derivative of this function here that we started with, okay? So we're going to practice using the chain rule with various different types of composite functions. And then after this, we'll look at some general rules that can be derived from the chain rule to help us deal with functions of these types. So let's start with this one. Y equals 3x minus 5. For this first example, for A through D, I'm going to do more work than I would normally do when applying the chain rule. And this is just to help us recognize the different parts of the rule. But after this example, I probably won't do as much work as I'm doing right now. Because ultimately you don't want to have to rely on all of these like supports. So when we're dealing with composite functions, it's helpful to think of one function as being inside and the other one as being outside. So here, again, f I'm thinking of as my outside, g I'm thinking of as my inside. So this guy right here has an inside, which I recognize as the stuff inside parentheses. That, in my notation up there, is what I was calling g of x. So I'm going to say g of x is equal to 3x minus 5. Okay, that sits inside what I'm thinking of as an outside function. And if you notice, that 3x minus 5 is being substituted in to this, which is being raised to the 59th power. So I'm going to define f of x as x to the 59th power. Okay, wherever g of x is sitting in this function, we're going to replace that with just an x. So it's x to the 59th power. So now I can think of y as f of g of x by writing f and g this way. So that y prime is equal to f prime of g of x times g prime of x. So at this point, I need to know what all of these things are, right? What is f prime? Well, f prime is 59 times x to the 58th power. That's my power rule. 59 times x to the 58th power. And what is g prime? Well, g prime is just 3, because if I take the derivative of this, all I get is 3. Okay, so now to find y prime, I plug this stuff in to this kind of general formula for the chain rule. Y prime is equal to f prime of g, so 59. And then instead of x, I'm plugging g in for that. So I get parentheses, 3x minus 5 to the 58th power times this 3 right here, because that's the g prime of x that gets multiplied right here. Finally, we simplify where possible. So 59 times 3, what is that? That's 177. 177. And then there's nothing else to simplify, really. 3x minus 5 to the 58th power. That is our derivative. Okay? Gotta separate the work there. Let's try another one. So f of x equals e to the power of x minus 6x squared. Oftentimes when you're trying to recognize a function as a composite of two functions, f of g of x, it's not uncommon for the g of x to be inside of a set of parentheses. So that's what we saw here. 3x minus 5 was inside of a set of parentheses. But that's not a universal rule that always works. We can't always determine what our inside function is just by looking for parentheses, because in this case, we don't have any parentheses at all. In exponential functions, though, whatever the exponent is, if it's something more complicated than just an x, then that is the thing that I'm going to think of as my inside function. So I'm going to call g of x x minus 6x squared. Like that. Okay. F of x is equal to e to the x. Remember, this is the outside function. So when I take g of x and I plug it into f of x to get f of g of x, This expression here, x minus 6x squared, is substituted in for the x here, and I get e to the power of x minus 6x squared. That's what we have right here. Now, I called this f of x up here, so I probably should have labeled these differently. I'm not going to worry about it too much, but that's something I normally would have done differently. So here, let's find our derivative of each of these now, since I know I'm going to need them. G prime of x is 1 minus 12x. Again, hopefully you've had enough practice with just taking derivatives of polynomials that you don't even really have to think about it much anymore. F prime of x, well, e to the x is its own derivative, so f prime is also e to the x. Okay, you know what I'm going to do? I'm going to change this to a y. I'm going to do the same thing over here, just so I don't mix it up with the f and the g that I'm using here. So if that's the case, what is y prime? Well, I'm not going to keep rewriting this chain rule every single time. I have it right here. So just kind of using this as a guide, f prime of g of x. So I write f prime, which is e to the x, but in place of the x, I'm plugging g into it. So I'm going to get something that looks exactly like my original function, e to the x minus 6x squared, but then I'm multiplying that by g prime. So that's 1 minus 12x. And this is fine to leave it this way. I wouldn't multiply that exponential function in, because then I would consider that less simplified, honestly. So I think that looks fine. All right, let's try another one. So here we have y equals the natural log of 4x to the fourth minus 7x squared plus 1. And in this case, I do have a set of parentheses, so that indicates that I should choose the stuff in parentheses as my inside function. G of x is equal to 4x to the fourth minus 7x squared plus 1. F of x is whatever's on the outside, natural log. And again, remember, wherever we chose g of x, that is going to be replaced with just an x here for my f. That way, when I find f of g of x, this gets plugged in for the x, and I get this original function back. Now I need the derivatives of each one of these. So what is g prime? Well, g prime, again, power rule, it's a polynomial, would be 16x cubed minus 14x. That constant goes to 0. What is f prime of x? F prime is, well, f is just the natural log of x. This one had a special derivative, 1 over x. We use this derivative a whole lot. The chain rule then would give me f prime, which is 1 over x, of g of x. So where the x is showing up in my denominator here, I'm plugging g of x in for that. So y prime is equal to 1 over 4x to the fourth minus 7x squared plus 1. And then I multiply that by g prime, 16x cubed minus 14x. This can be simplified just by taking this guy and multiplying it up into the numerator there. So I would write that as 16x cubed minus 14x all over 4x to the fourth minus 7x squared plus 1. That would be my derivative. Okay. One more to go. This one is another exponential function. Notice I had an exponential function over here, but in this case, the base is something different than e, and the exponent is not a polynomial, so it's similar but not the same exactly. What I'm going to do to start is I'm going to rewrite this as 5 to the power of x to the power of 2/3. Remember, the cube root of x squared is the same thing as x to the 2/3 power, but that makes that easier to differentiate when I want to apply my power rule to it. So now I identify inside and outside. We said before that if you don't have a set of parentheses, if you're looking at an exponential function, treat the exponent like your inside function, which we're calling g. So I'm going to let g of x equal x to the 2/3, so that f of x is just 5 to the x. Now we find some derivatives. G prime of x is 2/3 x to the negative 1/3 power. F prime of x would equal, this is your kind of a standard derivative rule with exponential functions. It's equal to the natural log of our base, which is 5, times 5 to the x. Let's put things into the chain rule. I have more space down here, so I'm going to go down here. What is y prime? Well, it's f prime, so this, of g of x. So I'm going to take x to the 2/3 power, plug it in for the x here, so that I get natural log of 5, 5 to the x to the 2/3. Then I multiply that to this g prime right here. So that's 2/3 x to the negative 1/3. This I could write differently. I could use the negative exponent to put something in the denominator. I could bring this constant out here. I'm actually all right leaving this one as it is, though. So let's go ahead and leave it like that. Okay? All right. Now, couple of notes. First of all, as has been the trend in this class, I gave you this derivative rule without proving why it's true. And if I'm perfectly honest, I have a difficult time with that because I like to know why things work the way that they do. And I do know why the chain rule works the way that it does. And if this were a full calculus class, we would walk through a proof of this. I feel like it's important to know why these different things work. It helps us to remember them better. And really, math, more than any other subject, is not something you should just take everything on faith. In math, if we're using a result, it's because you can prove it. However, because that's not really the focus of this course, the focus of this course is more knowing the rules and using them in practice, we're skipping an argument for why the chain rule is true. Your book kind of constructs sort of an argument. It's not really an argument. It's more of an example verifying it. But that's just kind of as far as it goes. I'm just stating that again. I know I keep saying that every time we do a derivative rule, we're not proving this, but I'm just stating it again just so you don't feel too much like I'm stating these things and giving you no idea as to why they would actually work the way that they do. If you are interested in knowing why the chain rule works the way that it does, you can go to my Math 400 videos on my YouTube channel. That's my full Calculus 1 class. I go through the proofs of all these things there. All right, enough on that. The other thing I was going to mention, which we talk about here, is that all of the derivatives that we just did fall into these kind of general categories, which the chain rule was used for. But if we kind of remember them in these more general rules, it helps us to take these derivatives a little bit faster. So generalized power rule. If I have any function of the form y equals g of x to a power n, and it can be any real number, it doesn't have to be an integer, then the chain rule would say that the derivative of this is n times g of x to the n minus 1 times g prime of x. Notice all that's happening here is we're treating this like the normal power rule, where you bring your exponent down and then subtract 1 from the exponent, except instead of having an x here, we have a g of x here. But then, because of the chain rule, we have to go an additional step and multiply this by the derivative of that inside function. So what I'm going to do from now on, when I'm encountering the power rule, I'm not going to break things down into f of x and g of x anymore. What I'm going to do is just apply this rule, bring the n down, g of x to the power of n minus 1, and then multiply by the derivative of x. We can do similar things for these other four kind of, cases, I guess. We encountered one of each of these in the previous example. So if you have a function that's of the form e to some g of x, then the derivative of that is the same thing, e to the power of g of x, because we know that's what happens with the exponential function. But then because of the chain rule, we have this additional factor of g prime of x that we have to multiply by. So that's where the chain rule played a role. This one, y equals b to the gx, where b now can be any base, not just the number e, is very similar. Y prime is equal to b to the power of g of x, so the same function, But remember, we also multiply by the natural log of our base b, and then because of the chain rule, we're also going to be multiplying by a g prime of x, the derivative of our inside function. The generalized natural logarithm rule is a very, very important one, and we use it a lot once we talk about integrals in chapter 4. But for this, if you have the natural log of some function g of x, then the derivative of that is just g prime of x over g of x. And we actually already saw that happen here, right? We had the natural log of some function of x. This is what we would be calling g of x on that other page. And the end result was g prime over g. Notice g prime is the derivative of g of x, the inside function, and then the denominator is just the original g of x, the inside function. So we're going to think through those types of derivatives just using that rule instead of breaking it down into an f of x and a g of x like we did in the last example. Finally, the generalized logarithm rule, if I have log base b of x instead of specifically the natural log of x, then the derivative looks almost the same as this. The only difference is that we also multiply that natural log of b into our denominator, because that's what we normally do for that general logarithm derivative rule, is we have that natural log of our base down here. Okay, so all 5 of these are all kind of special cases of applying the chain rule to a particular type of function, whether it's a power rule or like a power function composed with something, exponential or logarithm. So again, we're going to end this video here, but in the next one, we'll start looking at some examples where we use these. And like I have said multiple times now, I will no longer break these problems down into as many steps as I did in the previous example. In other words, I'm not going to identify the inside function and the outside function. I may still use those words, but I'm not going to write down f of x is this, g of x is this, especially since the examples we're about to look at are more complicated than the previous ones. So just to preview that before we actually get into it in the next video, notice here, I'm going to use my generalized power rule because I have a function to a power, but then I have another function to another power, and they're being multiplied. So not only do I need to use that generalized power rule, but I also need to use the product rule. So we're going to see combinations of rules that need to be used to take these derivatives. But again, that's going to be in part 2.